because it's going to go very quickly, and you might miss something. And if you miss something and you're lost, it might be a shame if you can't go back, rewind, and do it again. So I'm recording right now, and if everything goes well, I'll be uploading this. And I also have other recordings of preliminary material that you might want to go through. I will link to those when they are uploaded as well. So let's get started. Let's try this. Right. So the goal of this thing is to do a very short because it's only 1 hour, introduction to category theory. And the goal is to fix whatever is the current state of teaching category theory to new students. Because what you see a lot of times is lots of concepts, but without context or without proper motivation. And this time, what I will do, hopefully it will help in this regard, is frame this introduction of category theory, frame the introduction of those concepts using the Simply Typed Lambda Calculus. So this is a bit strange. This is a bit tailored to MSP because I won't go through the Simply Typed Lambda Calculus. I will assume that you're all familiar with it. I will very shortly describe it, but not very in very much detail. And then the other thing I want to show in this presentation is once you know those concepts, how do you use them? What does it look like to use them? Because you will see in the literature things like, this works because this diagram commute, and we're good to go. Let's keep going. We're done here. And then the paper or the book will keep going. But there's no real understanding of what does that mean? Like, how do you get to here? Sometimes you have diagrams that commute, but you don't prove anything. What's the difference between this and what I've just seen, right? And the book won't tell you this because, of course, they run out of space and time and they can't go through every detail. But there is a way you can experiment with those proofs, and that's to do it yourself in a programming language. So here on the left side, I have a programming language. It's Aegis 2. And I'm going to use it to show you what it's like to prove something through and through using the properties and the concept that I will introduce right now. So with that said, let's start with defining very quickly what is a category. So just like other properties in mathematics, like monoids, a category is about what things are and what property they have. So for example, monoids tell you that if you have a carrier set, in this case, for example, natural numbers, and a way to combine them, then the combining of them keeps you in the same realm, right? And additionally, you have special things like the empty or the neutral elements, which says things like empty plus n is n, right? Category theory is another one of these, or categories is another one of these, like monoids, that tell you something about mathematical objects and its properties. In this case, categories are composed of three things. You have the objects. So let's take, for example, natural numbers. You have the arrows that relate those objects. So for example, less than or equal. And you have rules about how to compose them. And we're going to call this sequential composition. And the rules are, and you have special arrows. For example, you have a identity arrow, in which case this will be the reflexivity property of less than or equal. And you have property about the composition. The composition has to be associative. So category is any mathematical object that has those properties. So if I write examples for our natural number here, I have that 1 is less than or equal to 2, right? And I also have that 1 is less than or equal to itself. And if I have a third thing here, 3, I have that 1 is also less than or equal than 3 by going through. 2, right? And here, if you don't feel like this is convincing enough, I invite you to look at the left bit here, which is the implementation in Idris of what I've just described. So you have, as a record, a way to combine objects, a way to generate an identity arrow. So this is an arrow from V to V, given any V. A way to combine arrows if their boundaries match. So here it says if you go from A to B and B to C, you go from A to C. And you have the property that composition is associative and identity doesn't do anything. I haven't said it explicitly, I've done it already, and this is also something you will see in the literature a lot, but you can represent this, and I think this is one of the great but the great thing about category theory, that is you can represent them as 2D graph. In a sense, I read this somewhere, someone said, category theory is just writing your equations in 2 dimensions, and that's a good way to describe it. This is an equation that relates 1, 2, 2, 3, and 1, 3 in a 2D plane. This is helpful because you might be stuck looking at an equation like f, g, h, but you might get yourself unstuck if you look at the graph f, g, h, right? So that's why we have this 2-panel thing here with the code on the left, which represent the textual equations, and the paper on the right, which represents our more standard hand-wavy intuition. All right, so that's it for basic categories. Now we're gonna very quickly summarize something that we all know about, and that's the Simply Typed Lambda Calculus. That's half intentional. I thought the brackets would be distracting. I can use my default color scheme, but it's black. Right. That is true. So let me quit this and go to this one, and here, and do vim section. Well, this is cat, and increase the font size a ton. This should be more legible, is it? Great. So let's quickly recap. Oh, that's not the right file. Let's quickly recap the Simply Typed Lambda Calculus. It's those 4 things. So we have types, either units or functions. We have contexts, which are basically lists. And the contexts contain types. And we have variables. And variables are not strings or names, but they are numbers that refer to their position in the context. This way, we can never have a variable that is never bound in a context. This is commonly known as the intrinsically typed lambda calculus. And we have terms here, which say that a term is either something that refers to a variable in contexts, or lambda abstraction, or application of a function to its argument. And additionally, we have ways of mapping those things together. So here we have a few things. Renaming, which map variables to variables. Mapping of terms, which map a term in one context to a term in another context, and substitution that says substitute this variable in this context. And we have all those facilities to move things around. So for example, this takes a renaming from a context that contains one thing to delta to the same renaming, but we can ignore the topmost variable. Yes. So that should be, I'm going to assume this is already explored material. If it isn't, I'll be available afterwards to talk about this. But the one thing I want to show with this is what are the properties that we're interested in representing with the Simply Typed Lambda Calculus. So what we want to do is find a way to represent all of this as objects and arrows in a category. And what we're going to do is we're going to represent types as objects, contexts as objects, variables in contexts as arrows from context to variables, and terms as arrows from context to variable. And additionally, we also want to represent those mappings here, and they will also be seen as arrows, but this time between contexts instead of context to type. So assuming we want to do this, and assuming this is the mapping, what are the things we need for this to work? So we need a way to talk about function types. We need a way to talk about variables, but variables depend on talking about types and talking about contexts. We need to find a way to talk about extending a context with a type, right? See, this part here says we have gamma and an A, and this means we have A. So we need to find a way to express this thing. And finally, we need to have a way to talk about those rules that say, if I have a function body that assumes that A is in context, then what I can do is abstract over A and say A will come later, and this is now a function type. And I also need those rules that say how to apply a function to an argument by saying, if I have a function type that expects an A and I give it an A, I get a B at some point. So we're going to start with how to express this property here, or this property here, which is the end, right? This allows you to add things to a context. And what we're going to do for this is we're going to use something called products. If I can find them here. So product is a way to describe what does it mean to extract two things out of one. And I lost my pen. Oh, that's a bummer. Whoops. How did I lose my pen? Okay, let's keep going with the text editor. So here I have an operator that combines two objects, they're called O, into a third object. We have facilities to tell us how to, from a product, extract one or the other component. If you're used to a programming language, well, any programming language really, which has pairs, this is saying take the first component of the pair or take the second component of the pair. And here we have the big diagram where things are happening, and that is saying if I have a third thing C and I can extract by any means F and G an A and a B, then there exists a most efficient, most minimal way of extracting two things out of it, which is the product A cross B. And this arrow here, I've hand-wavily said the most minimal, most efficient way. This says, for example, if this is another type in a programming language, this could be, for example, a triple, or this could be a record type that contains multiple things, and we're extracting two things out of it. But the best way to extract only two things out of it is if it only contains those two things, right? And this is what the product does. It says the most try to remove everything that's superfluous and package it into this optimal way. So if you have an address, for example, address may contain whoever is living there, what's the street name, what's the the building number, and you might extract the street name as a string, and you might extract the house number as an int. And what that means is that while those are valid projections out of the address, the minimal way of extracting a house number and a street name is to simply pair up the street name with the number, right? So that's what this is doing here. It's creating this arrow from C to A cross B by saying this is the best way to extract two things out of it. So interestingly enough, this is something I haven't seen mentioned enough in the literature. The essence of being a product is not to have two things, but it is to be able to extract two things out of it. It's not being two things, it's extracting two things out of it. And here you have very simple properties. Again, they will be seen as this diagram commute, blah, blah, blah. But what that means is if you have a gigantic object here that contains many things, and it turns out you are getting the product from it, right? From it to A cross B, and then you're projecting out the first components. Well, you didn't have to do all this work. You could have just kept using the original projection function, which is f. And I called this prod left because it's the left side of this gigantic triangle. And same thing for right. And the last thing is quite boring, really, but is very important. And that is the arrow in the middle is unique. That is, if you have another one, it turns out it's the same one. Alrighty, so that is products, and we're going to see how to use them to construct the interpretation of contexts for the simply typed lambda calculus. Now, products, they allow us to go to the next part, and that is exponentials. I'm going to bring up the simply typed lambda calculus here, and I'm going to cheat and do the opposite that the way you usually see it. And that is, I'm going to look at those rules, and I'm going to say, what do we need for those rules to work? So we need a way to talk about function types, right? So much like extending context, this is pairing up two things, right? It's pairing up an A and it's pairing up a B. I'm going to use the operator exponential to talk about this. Don't think of it as exponential quite yet. Think of it as just pairing up two things that we care about. But those two things, they're different than product because they have those rules attached to it. So here the rule is if you have a pair of gamma and A, and that goes to a B, you can take out this A and bring it to the right side. You can travel from the left bit to the right bit. And this will become one instance of this way of pairing up things. And this function, this property is described here as lambda. You see that here, if you replace x by gamma, right? And if you replace context extension by products, and if you replace a by y and b by z, you see that we have the same structure here. Like a and, gamma product a becomes x product y, goes to b, and here goes to z. And here we keep the same x on the left, but the y has traveled from the left bit of the arrow to the right bit of the arrow. So this property has been preserved through this rule. The other thing we want to do, we want to say if we happen to have something that is an exponential, and we happen to have the exponent at our disposal, we can extract out the b here. And this is this rule here, right? So this saying, if we have an exponent of something and it's paired up with the exponents, we can get back z. So this is a bit, cheating, right? Because I've just said, here are the properties we want, and here they are. Okay. The squiggly arrow is the arrow that says morphism. So this is, if I parenthesize this correctly, this is a morphism from this object, which is a pair or a product, to the object, which is Z. And there is a bit of, there's a source of confusion too. I can see the chat if I do this actually. Can the font be larger? Yes. I'm not sure if this fits in the screen quite as I wish it does. I think this is working now. Yes. Sorry about this. If you look at product, for example, you will see that here the operator that combines two things together has a colon in the middle, and you'll notice that here it doesn't have the colon. This is just my personal convention to say this is the field projection. And if you don't want the field projection, I have another definition here that assumes that the category is available. The category and the product are available to you, and you can just use it without doing the field projection. This is just implementation detail. The convention is if it has a colon inside it, it's a field projection. If it doesn't, it's expect something. I'm very lost with this. That is fine. The goal for me is to have an overview, like a very quick overview. And hopefully, if there's something interesting in here, you can go back and watch the recording. I think the recording, at least for this kind of material, is very important because things are moving very quickly and you need to go through the thing. Also, I left my pen and show the things I want to show on the right side. I'm going to grab a spare pen if that is okay. I'll just be right back. Yeah, this is very annoying. I can't find my spare pen because it's not in the pouch where I keep it, which is absolutely great. It's like you have a backup, and then you have to run the backup, and then the backup doesn't work. How do I deal with this? See, this is the kind of thing that does not happen during rehearsals. That I wish happened more often. Is it in here? It's not in here. Okay, whatever. You know what I'm gonna do? I'm gonna take this and I'm gonna cheat. So this is, there we go. You can see on the right, this is the description of things, and I'm just going to coast through. Oh, it's reversed. Does this work? Yes. I have it written up correctly. Oh my god, it's not working. There we go. I have it written up on the right, so now you can see the nice graphics as you see the text. All right, sorry about this. So we've lost a bit of time on exponential. That's why I have the timer on the bottom right, so you can see how, or I can see how well I'm faring in terms of time. So this is terrible. We lost a lot of time, but that's okay because at least we have a backup. So exponentials, here in the middle, you see it, we're docking off the y and we're putting on the right side of the arrow. The laws are this and the diagrams are this. I'm not going to do the diagram thing because we lost too much time, but think of it as those are properties to encapsulate how those eval and lambda rule interact with each other. So now we have a way to talk about lambda, and we have a way to talk about application. The last thing we need to do is find a way to talk about variables. Let me go through STLC. And the great thing about variables is that they depend on this variable type, and this variable type depends on gamma, right? And we've already said, well, this is simply a product. Now, the one thing we haven't said is that while it is a product, it has two cases, either the product case and this case, and we haven't said anything about this case. And this case will be referring to the terminal object of the category. So we have another construction here, which is the terminal object, which is simply an object that has nothing special, but it has nothing special in itself, except that it has an arrow from every other object to itself. So this is what I have on the right. One, it's called one here, is an object, has a 2-1 way of transforming any object to a morphism from V to 1. And it is unique in the way that if you have another thing that goes to 1 from an object, then it's the same thing as doing 2, 1, right? Fantastic. So now we can go back into our definition of simply typed lambda calculus as a category. So what this is saying in the next part, I will have access to a category with products, with exponentials, and with a terminal object. And here I have descriptions of how to go from one to the other. The typical way of describing this is you will just have unwaveringly saying you map types to exponentials and you map units to terminal, etc. But this is a honest to goodness implementation. And the great thing about this is if you put a hole here, you can ask your programming language, what is the type of this thing? And it's going to tell us everything you need to know. There's a type error later, but that's fine. So this is supposed to return an object, and we're given two things. And we're also given all those things. And from all those things, we know there is only two ways to combine two objects, and this either using the product or using the exponential. And here, since we are dealing with a function, we are going to use the exponential. So units maps to terminal. Again, I skipped something because this is going too quickly. Types map to objects. Contexts map to object, and the rest map to arrows. So those are the objects that correspond to the function types and the unit type. For contexts, the empty context maps to one as well, right? And the non-empty context maps to a product, which recursively interprets the additional context as an object itself and does the product to T. I had a nice illustration about this, but you can see a context as a product of a context and something, which itself on the left side has a product of the rest of the context and something, etc. So it's a large product, and at the end you have the terminal object, which is one. It's a gigantic list built out of products. Where is this? Yes, it's a mistake. I remember this. It's a mistake. Thank you for noticing. I noticed that yesterday and I said, it doesn't matter. I'm not going to use it anyways. I thought I fixed it. I must have done it somewhere else. But yes, it's a mistake. Things are lined up so that they line up correctly in the categorical semantics too. And this is something we're going to see with renamings. All right, so I hope this is intuitive enough. Now becomes the harder things. So variables in context, we have t in context gamma gets us to this thing. And this is the bit where the fact that this is a programming language really helps. This works. I'm going to have the interactive mode turned on. So if I put a hole here, I will learn something from the whole by having pattern matched on this variable here. Recall that an empty variable, that the variable 0 refers to a non-empty context which contains the variable that we're looking for at its topmost element, right? So this arrow here contains a lot more information. Namely, this context being not empty looks like this, which means this is actually a product of two things. This is what I've described here, right? The goal is now gamma cross t to t. And if you pay careful attention, you see that what we're doing here, it was just taking the t here and putting it to the right side, which turns out is exactly what pi2 does. So this turns out to be simply the implementation of pi2. As for this one, we can ask what is the type here. And again, we will learn something, and that is the context is again not empty, but here there's an underscore. This refers to the extra variable that we're creating when we are doing the successor variable. So when we're doing the successor variable, we're saying we have a variable in context. If we add another variable, we still have the variable in context. It's just further down the context. And we also have access to our variable in context. So our context, if I look at here in gray, we're given x, which is a variable t in context gamma, and we are asked to go to gamma and s to t. And there's no way to go from gamma and s to t directly, but there's a way to go from gamma to t by doing x, right? This is the last line here. Interp x goes from gamma to t. So if only there was a way to go from gamma cross s to gamma, we could combine those two steps together in a single one and go from gamma s to t. And there is a way to extract the first element of a product, and that is pi1. And there is a way to sequentially combine two things, and that is composition. This is the operator here. And this is recursively saying, please interpret the inner variable. And so again, if you think of this as a list of things, it makes sense, right? It means we are not done. We need to keep going. And this says, keep going with the rest. I don't care about this variable. Throw it away. All right. Yes. So this is done. We're not doing too bad on time, actually. Whoops. I fell asleep on the on the P here. So the brackets is a terrible hack. Yes, the brackets is a terrible hack. This is why all those things are called pure and are in different namespace, is to use the idiom brackets here, which are actually applicative brackets in Idris. This is just to make the syntax slightly more legible than if you were to use text, and also to make it closer to what we see on paper. So we can have a closer mapping, a mapping that is closer to a one-to-one mapping than if we didn't. So the answer, I guess, is yes. And it's not a silly question. It's a hack. Right, so we said terms are themselves mapped to arrows, and the arrows go from the context in which the term is declared to the type that it has. So on the left side, we have gamma turns title t, and on the right side, we have gamma arrow t. And again, this is a case where we're going to match on this, and this will teach us something about the goal, right? And here, I can just show here on the right. When we have a variable, we learn that x itself is a variable, but we have just defined a way to talk about arrows when they are variables. So we're just going to defer to this definition, say, please interpret this arrow as the interpretation of the variable x. For lambda, we have a bit more a story that's a bit more complicated. So if we look at x, we learn that, and I'm gonna comment this out and ask what's the type here. And again, there's a type error lower down the file. If I ask the type of this, I see that x assumes that there is an A in context and results of something of type B. This is what I have here. I'll just have named S and A and B, S and T. It also means our goal now has changed, because our goal is something goes from gamma to a function type, right? Remember, function types are interpreted as exponentials. This is what I have here, right? This function type is actually the exponential from t to s. And now the question becomes, is there a way to go from this thing on the left, gamma s to t, to this thing down, which is gamma to the exponential? And the reason we're interested in this is because, well, x has, if you interpret this as an arrow, the arrow from gamma and s to t. And indeed there is. It is the lambda property of the exponential, right? So this I've just written it here, but it's repeated here, right? Lambda docks the y off the product on the left and puts it on the right side of the arrow, on the right side of the relations, right? So that's very handy. So this is just lambda of interpretation of x. So here we are. Now for the application, this is again an area where asking the compiler, what am I supposed to do here? This is very complicated, but I've written here the context. And I'm going to ask it, and it's going to complain because, of course, now it cannot infer what those are. But no matter, we are going to look at this, and this is actually unreadable. So is there a mistake somewhere? It looks like there is a mistake somewhere. This is the mistake here. Fantastic. So it looks like we don't have much to go on here. We are expecting an arrow from gamma to t, right? Which is the result of the application. And we're given those two arrows here. In reality, we're not even given those two arrows. It's just that I've put them in, I've made them available. But we're only given x and y, which are repeated here. So x is a term that is of type s to t, and y is a term of type t. And there is no immediate way of figuring out how to transform those things into a t. However, I think I have a nice diagram here. Well, nice. I have a diagram here. If we interpret x and y, we realize that they denote two arrows that come from the same object, gamma. And the one of them goes from t power s, and the other one goes to s. If we do the product, if we use the product using those two arrows, we get an arrow from gamma to t power s cross s. This works because they both come from gamma. Like we're extracting a t power s from gamma, and here we're extracting an s from gamma. And if we pair them up, we're extracting those two things. Sorry, not extracting, but we are representing this gamma as the one thing that interests us, and that is t power s cross s. And now this might be easier to digest, right? Because there is a rule that allows us to take this statement and turns it into a t. And this statement is, or this arrow is a val, right? So this is what this implementation here is doing. It's taking the product of x and taking the product of y and composing it with eval with the hopes of obtaining this arrow here on top that goes from gamma to t. And this is what this implementation here is doing. So this operator is the product. This is, again, sequential composition, and this is eval. All right. Now we have the big things, renamings. So renamings allow us to map oh no, that's my alert to say it's late in the evening and work hasn't started. Work better start now. So this as if I have a variable in context delta, I can explain every single one of them from gamma. And this is represented as an arrow from delta to gamma. Now we don't really have much to go on here either, right? Because renamings are just functions. Renamings are just functions. But what we can do is we can match on either the context gamma or the context delta. We're going to match on gamma and see what we get. So here, if we match on gamma on the right side, you'll realize, well, the interpretation of an empty context is the terminal object. And we already have a way to construct any arrow to the terminal object, and that is to use 2, 1. So this is what we have here. Now we have another problem for the non-empty context, and that is now we need to figure out a way to construct an arrow from delta to this product, right? So typically the way we construct arrows to product is we find an arrow from delta to this thing, and then an arrow from delta to G. And then we simply use the product operator. So can we find an arrow from delta to G, right? On the right, I've called this goal 1, and on the the other one is called goal 2. So delta to G must be a variable, right? A variable in context delta. It must be the variable G in context delta. And delta to gamma must be a renaming of delta to gamma, right? Those are the only two ways we can construct things. So are there values of those types? And if we look at our contexts, here, ren is a function like this. But if you think of it as a renaming here, I've written it as f here. It's a renaming from delta to gamma and G. So if only we could dock off the G, we would get a renaming from delta and G. And we do have a function that does this, and it's called shift, right? So here I've written it, and in the paper on the right it's called forget, but in the program it's called shift. So here, if I get the type of this, we do have here the clear relationship where you have gamma and G goes to delta, and here we want to dock off the G from this. So this is, oops, this is shift of renaming. All right, and we compile this, and it's happy. And now what about this? So this is saying we have a variable G in the context delta. So this is a bit more tricky. We have to come up with a variable. We have to figure out which variable, how to create a variable in this context. But we don't have anything. We only have renamings. So we have to work with this. Just a sec. Where's this thing? Here. Yes. So we have to work with this. So what we're going to do is we're going to notice that here, renaming is a function that creates a variable in context delta, provided we give it which variable it's supposed to be. So here the variable it's supposed to be is G. So we're going to type ren of G, and then tell us what else is needed. And the last thing that is needed is a variable that is available in context as the topmost variable, right? And we already know what this is. This is 0, right? 0 is the variable that is available at the top layer of the context. And if we compile this, the compiler is happy. And if we inspect our goal again, well, we are given now those two there's two things. So this renaming from, this renaming from gamma to delta and this variable from delta to g. And if we do the product of them, so this is prod.prod, and I think this should work, pure P1 and pure P2, we get the arrow that we were looking for. And no, it's not working because it wants this to be this, and it wants this to be, wait, that's correct. Renamings and variables. There we go. Right, so you can see how you can get to those concepts by going back and forth between the paper definition and the program definition and asking the compiler, please help me go through this, please. And we have last one thing, but we won't have time to talk about it, and that is substitutions. And now we're going to go through the big one, which is a theorem, right? So this is going to showcase. So we have seen. So we already have seen half of what we wanted to show. We have seen the basics concept of category theory. We have seen basic constructions, and now we're going to see how to use them to prove useful things. One property that we want to ensure in our Simply Typed Lambda Calculus is that if you get to the paper version here, if you apply a renaming on a variable, that should be the same thing as interpreting the renaming and then interpreting the variable. It might be more clear to see here, but if you draw the diagram, is the diagram here? There we go. So those are called sub, but they should be called ren for renaming. But if you have a rename from delta to gamma, and you have a variable t in gamma, then doing the renaming of the variable and then interpreting this as an arrow should be the same thing as interpreting the renaming and then interpreting the variable. But again, we only have this diagram to go on. How do we prove that this diagram is true or contains truth, right? And this is where going through a programming language helps a lot, because now you can pattern match on the variable and figure out what is what. So if my variable is 0, I have a hole here, right? And I can ask the compiler, what is supposed to happen in this case? And in this case, it's going to tell us that we have at our disposal ren, but its type has changed. It's not from delta to gamma, it's from delta to gamma and t. And this is because a variable is, as mentioned here, a variable 0 is always in a non-empty context, and moreover, the type of the variable is the topmost type in the context. So pattern matching on this has changed the diagram quite a bit, right? Now our diagram looks like this. So on the top, we still have our renaming, but on the right side here, we have a product of the context and the type that is supposed to be the variable. And here we have a substitution with a renaming with 0. And all of this can be retraced back to our previous definitions, where this interpretation of the variable 0 is actually pi2, right? And you can see it because it takes this pair and maps it to the second element, t. This thing is the product of something that I've called f and sub of the variable, which is 0. So renaming of the variable 0. And we actually know what this is because we just defined it. This is this thing. This is this product, right? And finally, we have the interpretation here that is the lone right side of our triangle, which is simply apply the renaming to the variable 0. So if we pay careful attention to this diagram again, you'll notice on the top right here we have an arrow that goes that is pi 2, and here we have a product of two morphisms. So this looks suspiciously like, I'm gonna find the proof, looks suspiciously like something we can use here, right? The right property of the product. If we can prove that our arrow here, which is exclamation mark, is actually F2, well, a product of F1 and F2, and we project out the result with pi 2, we can prove our statement. Wherever it is, where did I put it? Here. But this is already the case. Actually, I've just written it down, but this is already the case because this arrow here, which is the product, is already a product of f of something we don't care what it is, and sub 0, right? And sub 0 already appears here. So this is really the right property of the product triangle. And if we write it down here, or rather, if we look at the type here, we see that Idris has already figured this out for us. We don't actually have to think too hard about this. It says this is the composition of this product and pi 2, right? And the second component of the product is actually the right side of our equality. So this is simply prod right. And there we go. And now for the final bit, which is a more complex proof. I've put the diagram here. I already also have the proof on paper on the right here. So now we're matching the variable, and the variable is further down in the context. So this is indicated here by saying gamma is actually gamma and s, and the type here is t. So t and s do not unify to being the same. And here I have already put two things into context. I have the induction hypothesis as IND, and I have proof, which is simply a proof that the implementation of the renaming of a successor variable is the shift of the renaming of the variable. This is a proof that is proven in the Simply Typed Lambda Calculus file. Okay, we're almost there. So this big triangle, if we rewrite this here, what this is stating, and again, like I flip things around a little bit. But what this is stating, wait, I'm confusing myself now. So this is sub, this is this, and this is, and yes. So the new type of this thing is saying, if you apply the renaming to the variable s of x, this is the same thing as composing, first of all, the product of this and that, which comes from our definition of renamings, with pi 1 and with pure x. And if we draw this as a diagram, it is this square here. So this is the renaming applied to s of x. This is the product, which is defined here. This is pi 1, and this is x. So now we need to, if we have a way to glue those two triangles together and figure out what the diagonal is here, then we can just glue them and say this property works because this square commutes, and this square commutes because those triangles commute. Again, this is part of where working independently type is a bit painful because you have to do all those steps manually, but in terms of teaching, might help you understand what the book cannot communicate, and this is how things line up perfectly to work out a proof. So the two triangles, turns out that the diagonal here needs to go from delta to gamma, right? And the only way we have to do this is through a renaming from delta to gamma. So is there a way to get a renaming from delta to gamma? And if you look at our context, here we have a rename from gamma s to delta. And we already know that there is a function that allows you to dock the s out, ignore it, and that is shift. So shift gives us a renaming from gamma to delta. And this is what we're seeing here. What we're doing here is calling the induction hypothesis on shift of the renaming and using it on the variable that is lower down the context. Basically saying, keep searching for the variable and prove that this works for once you find it at some point. And the other thing to notice is the induction hypothesis almost has the right type already. It ends in wait a minute. It has this bit here, right? Which is this bit here and pure, right? It looks close, right? You have pure here, you have pure here, you have shift-ren here, you have shift-ren here. You just need to like fiddle with this middle bit to figure it out, and you need to figure out this right bit here. And again, if you draw the induction hypothesis as a triangle, you see it's actually this triangle here. The induction hypothesis is here. So now we need to figure out what this triangle is. And again, we see that here we have a triangle that is a product followed by pi1, which means if this aligns with this diagonal, then we are done. Unfortunately, so we're going to call this function glue triangles. I'm going to put it here. Unfortunately, if you do this, prods.prod left, you will see the types don't quite match up. And this is because the diagonal doesn't have the right type. So here you end up with shift of the renaming followed by pure is the same thing as applying renaming to t. This bit here is actually taken care by this, but the left bit we don't know. However, again, if we look at our context, we already have by induction hypothesis this bit. So now we need to stick on here on the left side of this equality, then stick this in the middle, and like stick it to this part on the left, and we end up with the right side of our equality. And this is simply a transitivity operation. So we start with the induction, we do trans, and then we have the right side. And again, what this is doing is this is carefully matching up the diagonal so that it looks like exactly what we're looking for. And now what we're left with is this property that is simply, this is just extracting the implementation of ren, the implementation of shift so that we can see it. But this is simply, and this is simply a congruence on pure and then this proof here. So this is cong pure of proof. And if we type this, it doesn't work because there's a typo. And here we are. Please work. There we go. All right, I'm out of time. What have we learned today? We have speed run through basic definitions of category and some properties that are useful, like product, exponential, and terminal objects. We have seen how those become useful for interpreting the Simply Typed Lambda Calculus as a category. And we have seen how to use those basic tools to write proofs using both paper intuition and a theorem prover programming language that gives us information that would otherwise be harder to see or understand. More specifically, the program will complain very loudly if things don't match up perfectly, which is something that you need to think about when you're doing those proofs. When do things match up perfectly? When do things don't match up perfectly? The paper won't tell you, but the program will. Thanks for listening. Do you have any questions? And I'll stop recording.